Hi everyone, thank you so much for coming to my talk today. I sincerely apologize that we have to give this talk online. Due to reasons that are beyond our control, we couldn't make it in person. And I sincerely thank the organizing committee for accommodating the situation. So let's get started. What I'm going to talk about is time-dependent Hamiltonian simulation. So as you can imagine, this will be a quantum algorithm talk. It will consist of two works. The first work is joined with these two collaborators, where we will design a quantum algorithm together with the circuit and general complexity estimate. The second work is joined with these two authors, where we will dive into a very intriguing behavior of the algorithm, so-called superconvergence, where we were able to provide a rigorous proof on the fully discrete case. So let's get started. Here is the outline of my talk. I will first just briefly mention time-dependent Hamiltonian simulation, the motivation, and the existing algorithm, review a little bit of the state of art, and raise a question that we would like to answer, and then introduce my work. So time-dependent Hamiltonian simulation, well, of course, this will be a very familiar topic to the audience. And what I just want to say is that for the purpose of the talk, in most cases, we are going to deal with the time-dependent Hamiltonian in the most general form, so that the exact unitary become a time-ordered exponential to compensate that the Hamiltonian at different time may not commute with each other. And the point I would like to convey is that the underlying difficulty of this problem really increases as the unitary become more and more highly oscillatory. What do I mean? So there are two sources of oscillations. First of all, one can imagine if the operator norm itself is getting larger and larger, the unitary is wrapping around itself very, very fast. Or equivalently, you can view it as rescaled time for a longer time scale. One would expect to have more cost to resolve the proper dynamics. Similarly, if the operator H is time dependent and is rapidly changing itself, then we would also expect increase the cost to resolve the proper dynamics. So correspondingly, there are two challenges or two enemies. One is the operator of the Hamiltonian. One is the operator of the derivative, which captures how fast the oscillation is. Before I dive into the state of art, just to mention that highly oscillatory dynamics is really everywhere. There are a few pictures, as you can see here. However, if you're primarily mainly interested in a Hamiltonian that is in the time-independent form, you may wonder, like, okay, D, why do I care about time-dependent Hamiltonian simulation? Well, I would like to say, even in that case, it may also be beneficial for you to consider time-dependent Hamiltonian simulation algorithm, because one can typically change the time-independent problem into the interaction picture and gain an improved complexity in many scenarios. So even if we are dealing with a time-independent Hamiltonian, considering a time-dependent Hamiltonian simulation algorithm may still be interesting to you. So I will revisit this interaction picture later in my talk. So now just a little bit about the state of art. First of all, when Hamiltonian is time-independent, I think the most celebrated algorithm in Hamiltonian simulation is probably trotterization. It's so celebrated to the level it has different name. We call them trotterization, product formula, time splitting, or operator splitting. Nevertheless, they all mean the same thing. Let me demonstrate the idea using just a sum of two terms. Well, the trotterization states that instead of computing the whole Hamiltonian, we just chop the time into small pieces. On each of the pieces, evolve H1 or H2 alternatively. This is certainly an approximation come with an error. It is governed by the operator norm of the Hamiltonian. However, due to the celebrated works in this field, we know that trotterization actually has a very nice commutator cancellation. Instead of depending on the operator norm itself, the error actually depends in a commutator form. Correspondingly, the cost will also be a commutator form. You may wonder, why is commutator scaling any good? Just a simple example, although this may not be an interesting Hamiltonian to you, but to illustrate the point, I have a position operator plus a momentum operator. The momentum operator is a differential operator that is unbounded from L2 to L2. That's where the wave function lives in. So if we look at operator norm, it's going to be infinity. However, if we look at the commutator, it's as small as 1. So in many cases, if you can gain commutator scaling, it can give you additional cancellations that can do you wonders. The second other types of algorithm, I will group them together to call them post-trotter algorithm. For all of these algorithms, the cost will have a polynomial dependence on the operator norm itself. The high-level reason is really that these algorithms will need an implicit or explicit form of somewhat block encoding, and the subnormalization factor is upper bounded by the operator norm. That's the reason for this. Now let's look at the general time-dependent Hamiltonian. You may wonder, is there also a trotterization? Of course there is. Instead of involving H1, H2, now we are going to pick a specific time to involve them. This is a so-called standard trotterization. So due to this very celebrated work, one know that this standard trotterization actually has a cost that is polynomially dependent on the derivatives. So the higher the oscillation is, the more cost, severely more cost you need to pay. On the other hand, you may wonder, if time-independent trotterization gave you commutator scaling, wouldn't the time-dependent case it also give you commutator scaling? Well, here is a simple illustration where I'm taking the Hamiltonian in a controlled form with H1, H2 actually commute with each other. Suppose there is indeed a commutator scaling, like our previous case, the error becomes, the formula becomes exact. So if we run it, I should see machine precision instead of some large errors. So this demonstration immediately tells us the standard trotterization in the general time-dependent case actually do not give you commutator scaling. If you work in this field long enough, you must have heard the so-called generalized trotterization, which instead of saying I'm directly simulating each of the subtimes, so it states that I'm turning this time-dependent simulation into this should be approximate to other time-ordered matrix exponential. What I want to say is, first of all, as you can see, the right-hand side is still two time-dependent exponential. In other words, there are still two time-dependent Hamiltonian simulation algorithm. It's typically when you further implement each of this time-ordered operator is where the potential commutator scaling can get destroyed. The second remark I want to make is that for the generalized trotter, indeed one can show, as we proved earlier in our work, that low order will have commutator scaling. However, as recently in this very interesting work in QIP, they show that when we raise this generalized trotter to arbitrary high order, we will also encounter polynomial dependence on the derivative. So more generally, for time-dependent Hamiltonian simulation, there are these trotterized algorithms where we hope to get commutator scaling, but they do not quite give us commutator scaling in the general time-dependent regime. The second type of algorithms are these randomized algorithms, Dyson algorithm, where they suppress the derivative dependence, unlike trotter will have a polynomial dependence on the derivative. However, the randomized algorithm can only do first order. It's typically difficult to go beyond the first order. And none of these algorithms actually give us commutator scaling in general time-dependent case. So now I would like to summarize. There are two sort of challenge or enemies. Correspondingly, there are two nice features. And our question here is really that, can we have a commutator scaling? Can we design a quantum algorithm that we show that our algorithm have commutator scaling for general time-dependent Hamiltonian simulation? On top of that, I would also like to have weak dependence on the derivative. So imagine if I make a wish list to the type of features I would like to have in a time-dependent Hamiltonian simulation algorithm. I would like to have two features. On top of that, I hope our algorithm is high order in the sense that it's at least beyond the first order, as that's what is typically expected for randomized type of algorithms. So here is our contribution. Our first contribution is that we propose a family of quantum algorithms that are based on Magnus expansion. It has both of the two nice features, and it is of second order in general, which is beyond the first order. As you can put our algorithm back to this table, and you can see all of the nice features in comparison with other great state-of-art prior works. And our second contribution is that we find our algorithm have a very intriguing and surprising behavior, so-called superconvergence, which means that in a specific Hamiltonian, in a specific scenario, the algorithm dramatically outperforms what it is expected in general. In our second work, we provide a rigorous proof in the fully discrete case using discrete micro-local analysis, and the proof is very interesting and highly non-trivial. I will present it a little bit in the end, the high-level ideas. All right, so now here comes to the idea of our algorithm. Recall our target is that for general time dependent, I want to have commutator scaling. Now it's natural to think in the time independent case, for example, why do trotterization have commutator scaling? The high-level intuition, although it's not a proof, is really that we have this so-called BCH formula, which guarantees there is a series expansion where all the higher order terms are in the nested commutator form. So it's natural to ask ourselves, in the general time-dependent Hamiltonian, is there a series expansion to deal with this exact unitary, where we can have a series where all of the higher order terms are all in the nested commutator form? The answer is yes. This series is exactly the Magnus series, which is a very celebrated topic, has been used to design classical algorithm and also be widely used to analyze physical phenomena for physical system as an analytic tool. So here is the series expansion. As you can see, Magnus is essentially stating that I'm going to drop the time ordering and going to write it into a matrix expansion without time ordering. And then we will have a series of many terms where all the later term will be in a nested commutator form. So at the very beginning, it seems that we are in a good shape. So the second thing is to design an algorithm. What we are going to do is to truncate the Magnus series at a certain order. For our work, we truncate at the second order. There's no particular reason to truncate at a specific order. In our later work, recent preprint, we can truncate at an arbitrary order. However, just with caution that the arbitrary order, one may expect to have some factorial dependence in the order that we are truncating. Nevertheless, in our new work, we got rid of that factorial dependence. Nevertheless, let's focus on the second order for the purpose of the talk. Then the second order Magnus is essentially writing a bunch of integrals. Now, how do we deal with these integrals? We are going to revoke this simple Riemann sum, which is typically used in Dyson series expansion as well. But now here you may wonder that it really doesn't make sense. Isn't that the Hamiltonian itself, as I said, is oscillating very fast in time? So isn't that the number of quadrature points I need to properly resolve these integrals needs to be gigantic, needs to be as large as how fast the integral is, how fast the Hamiltonian is oscillating. That's indeed the case. However, for this type of sum, it turns out we can design a very simple LCU type of circuit to bring the cost into log m, where m is number of quadrature points. So we can safely enlarge the number of quadrature points without paying a large cost to the algorithm. This is also why our algorithm, in the end of the day, will have a log dependence on the derivative. So there are two questions typically associated with a quantum algorithm. One is how to implement what is the new circuit. The second is what are the errors. These two correspondingly will give us the complexity analysis. So first of all, as I advertised, the corresponding LCU circuit we can do, it's not, I would have to admit, it do not look very user-friendly, but nevertheless, the point is that we get away with only log of the number of quadrature points that we are using. The second is the corresponding error, the error analysis. There are two approximations made. One is quadrature, where as you can see here, we can choose the quadrature numbers as large as the derivative and only pay a derivative cost. The other type of approximation corresponding error is coming from the Magnus expansion, as we can rigorously prove that the Magnus expansion actually has a commutator scaling. So combine the circuit and the error analysis together, this gave us the overall complexity. First is the pure complexity to the Hamiltonian itself. As you can see, we have commutator scaling, and the two qubits, we have a log dependency in terms of the derivative, exactly as what we claimed at the very beginning. So now I would like to dive a little bit into the complex analysis a bit more. You may wonder that, okay, D, now I have commutator scaling. I have second order as what I showed you before. You may wonder, like, why can't I do, isn't, because I have commutator scaling, I could do better. Can we just do better by making a Taylor expansion? And then the leading order term will all get canceled. Instead of a first order, second order, you get an additional H, which gave us third order in general. Well, you can do that, but pay attention. In doing so, you introduce the derivative dependence. Actually, if we go back to the error representation, we can write out the exact error representation of our algorithm involving 11 terms. If you do the calculation much more carefully, it turns out you can have additional cancellation, which will give you actually a false order accuracy. However, we will have to introduce, if instead of second order, if we say the fourth order, the constant dependent, the pre-constant factor dependence will be polynomial dependent on the derivative, which is precisely what we want to get rid of. If you recall, we really want to have log dependence on the derivative. Now you may wonder, okay, Dee, but why do I care about so much about the derivative dependence? Maybe it's polynomial dependence on the derivative, it's still okay. Let's recall at the very beginning, I said one of the motivation to consider time-dependent Hamiltonian is interaction picture. So we indeed want to have an algorithm where the derivative dependence is mildly so that we can accommodate for interaction picture. So now I gave you a concrete example. For example, this is so-called unbounded Hamiltonian simulation or real space Hamiltonian simulation problem, where I have Laplacian plus potential. This problem is so-called unbounded is because the Laplacian is a differential operator from L2 to L2. Its operator norm is infinity. So the unbounded nature really give you if your algorithm depends polynomially on the operator norm itself, you really cannot see any all the complexity become trivial bound, give you infinity. However, you can argue with me that even on classical computers, we do not directly simulate unbounded operators. We always discretize. What's the big deal? I'm illustrating it with only one-dimensional example to give you a sense. So the size of the matrix or the size of the Hilbert space is a capital letter N, where N is the degrees of freedom I use for spatial discretization. However, as you can see, the operator norm sits polynomial in N. In other words, after discretization, due to the operator norm dependence, we will get a complexity that is of poly N instead of poly log N. That is what we are really hopeful. As this problem is really time independent, Hamiltonian simulation, you may wonder, okay, Chotter has nice commutator scaling. Why don't I just use Chotter together with time-independent commutator scaling result, and it will guarantee to give me a better cancellation. Yes, it indeed gave us good cancellations, but not sufficient. All these nested commutators will still have poly dependence on N, which will not give us polylog. So in order to open the possibility of polylog, we really need to move into the so-called interaction picture, which turn a time-independent problem into a time-dependent one. You may wonder, it seems that we are making the problem more complicated. Why should we do that? As you can see, if we're only focusing on the operator norm itself, the A is unbounded part that is associated with capital letter N is really dropped. We are left with B, which is the sort of the bounded part. However, the challenge is that the derivative norm is very large dependent on A. We really need a log dependent or big dependence on the derivative so that we do not reintroduce this independence back into the estimate. So our algorithm, as we said at the very beginning, we have commutator scaling. We also have log dependence on the derivative. So our algorithm is perfectly fitted to be applied to this particular application. So now let's see what happens. So for this part, as I said before, we will have a log dependence on the derivative, which will give our log n cost. So to have a polylog n cost in total, all I need is basically to say that this parameter is actually dependent only on B, and then I'm done. By the way, this H squared states that our algorithm is second order in general. I would like to give you 3 seconds to quickly convince yourself this is actually trivial. So, I mean, the operator, these commutators, it's bounded only by B. Yes, this is actually trivial. We can just immediately get this bound. So what we immediately get is that we will have a second order algorithm with n independent cost the error parameter. In other words, we have a second order polylog n cost algorithm for this particular application. However, that's not what I'm going to claim here. What I'm going to claim here, the so-called superconvergence result, is much stronger. I'm going to say that for this particular application, instead of second order, we actually have fourth order. On top of that, very importantly, the error per constant, we can still show it's independent of n. So despite the Hamiltonian itself is really oscillating at the scale of n. So this is very surprising result, superconvergence, which means that the algorithm convergence performs dramatically outperform what it is expected in general for a particular application. So this is our results. here is some numerical evidence. As you can see, now my algorithm is fourth order, so I'm comparing it with a fourth order. You can use the classical Magnus algorithm, which I'm using here, or you can use a fourth order trautorization. What you will see is that our algorithm remain uniform in terms of n, however, other types of algorithm really do not. Okay, so here comes the key commutator estimate. It turns out we proved this sort of very surprising results using high-level mathematical tools where we designed a new framework combining the discrete microlocal analysis with two-scale simple calculus. The point is that we can prove that this Nasse commutator scaling actually gave you another h squared, which makes the second order fourth order. On top of that, as long as this condition is satisfied, the initial the constant is uniform, is totally uniform in terms of n. So this is what we were able to show. Now you may stare at this this condition. You may like, well, it seems that you are introducing a new condition. But I want to emphasize this is really not a new condition or not a restrictive condition. It's because recall we are precisely trying to justify that the time step size is much larger, can be taken much larger, should not be refined by the size of the spatial discretization n. This is precisely in that regime. As you will see very soon, it's in the composite of the Taylor expansion regime where your time step size needs to be tiny in order for the Taylor argument to work. Okay, here is just a numerical evidence to show you what we rigorously prove is indeed what you expected to see in practice. So now in the remaining time, I'm going to give you a high-level idea of how we prove the superconvergence, starting with a fake proof that do not work, but hopefully give you a sense of why this result is indeed non-trivial. So let's look at the one layer of Nasse commutator. There are more terms to be done, more work to be done for multiple layers, but one layer to begin with. Imagine we do a Taylor expansion. Then the first order term BB commute will be gone, so we will be left with BAB, and which coming out with S. So one layer commutator gave us 1s, maybe two layer gave us 2s, which gave us two additional orders. You may think that, oh, I prove your superconvergence in just one line. However, what I want to say is that this argument is very far away from superconvergence. It's because all of the remainder term, you can plot them numerically, you will see that the remainder term are not uniformly bounded in terms of n, which means that the Taylor expansion argument is really a no-go. So now what do we do? So we first designed a continuous intuition to justify this algorithm where we use this phenomenon, where we use this pseudo-differential calculus Weil quantization, which means that this is really our regular quantization, means that if I have position, we will have multiplication. If we have momentum, we will have a differential operator. Then if we look at the second term, it turns out we can rigorously rewrite it as the Weil quantization of this one operator. This is result series truncation. This is exact. And this is a so-called exact Ogolev theorem. And then we can plug it back in, since now we have the commutator, in other words, Lie bracket. Semi-classically, there is very nice analogy between Lie bracket with Poisson bracket. Poisson bracket take x derivative and p derivative coming here, so we will get s coming out because of chain rule. So on the high level, if our derivatives are bounded, we have the superconvergence result. However, I want to emphasize this is not what we present in our second work in the discrete proof, because this proof, although very nice, is not going to work at all in the discrete case. As you can see, the key argument is really this exact Ogolev theorem. Now, you may wonder, after discretization, does exact Ogolev theorem hold? So first of all, after discretization, you are working with matrices. You cannot use these PDE tools to prove theorem. Nevertheless, in our previous work, we have a result showing that the underlying matrices can be identified as Weil quantization or quantized torus, and then the matrices operator norm can be upper bounded by the L2 to L2 norm continuous object. So we only need to work with the continuous object, which are very easy to work with, to give us the discrete bound. So this is the first thing, but this is only a tiny step. It doesn't resolve the mean difficulty. The actual mean difficulty here is after discretization, exact Ogolev theorem no longer hold. We can still utilize a so-called approximate Ogolev theorem. However, in the mathematical analysis literature, the approximate Ogolev theorem only holds up to the so-called Ehrenfest time, which is of the order log of n. However, if you look at the matrix that we need to analyze, it has n squared. So we are working with a time scale that is much longer than log n, much longer than what the Ogolov theorem is supposed to hold. So this is really the mean difficulty make our problem vastly more difficult compared to what one would naively imagine. So it turns out there was the two simple class parameter, a number of theorems from this very nice annals work that we can utilize. Together we can prove our result on a rigorous manner. I'm not going to tell you precisely how we prove our result, but just as a high-level remark, so what we were able to prove utilizing this is really in the opposite regime of Taylor expansion. We can justify when the time step is super, super large, we can still yield meaningful and uniform estimates in terms of the parameters. And very importantly, this is very nice application because prior, we always know that micro-local analysis, semi-classical analysis is very applicable when the problem itself is in the semi-classical regime with some small parameter. However, our problem is not in a semi-classical regime. Nevertheless, due to the spatial discretization and time discretization, we can extract a mathematical semi-classical problem underlying and to prove it using mathematical analysis. This kind of application is also new in the literature. So now I can summarize. Here is a sort of the summarize of our work, and we also proved the superconvergence. For the ongoing, I also mentioned a little bit in the we have a preprint regarding arbitrary high order Magnus. The challenge is that for arbitrary high, suppose I truncate at piece order, naively you would directly extend our current circuits. We will introduce a p factorial cost dependent. However, in our new preprint, we can get rid of p factorial entirely. We can show it's poly p actually. So that's all for today. Thank you so much for your attention, and I really appreciate you coming to my talk.
So we can take some questions.
Thank you for the talk. So in between, when you show the circuit for the algorithm, did you use the LCU technique for it?
Yeah, that's right. So the idea is that for the Magnus series expansion, we will drop the time ordering. So the time-dependent problem will become essentially a time-independent problem with a new Magnus Hamiltonian, if you would like. So the new Magnus Hamiltonian will have sum of a number of terms. So the first thing that we do is to use a LCU-like circuit to devise that term. So that's the circuit that I was showing there.
Okay.
Yes.
So then it like not necessarily become a product formula type of technique, and so
yeah, that's right. So this is not a product formula technique. If there are a number of works recently by a number of people in both industry and academia. People have tried to further pair with Magnus series with product formulas. So over there, if you further decompose it into product formulas, then typically, say the commutator scaling that we are trying to get here, you cannot get that, and also there might be some further derivative dependence unless you are looking at particular Hamiltonians. So if we do the further approximation by product formula, some of the nice property can be lost.
Right. So a follow-up question. So can we use sampling-based LCU technique to get rid of extra ancillas if we not care about preparing the state, but just caring about measuring expectation value of some observable on it?
Yeah, sure. I think that is possible. So actually, regarding getting a smaller number of ancilla qubits, there are some recent work by Andras, Gideon, and so on, and collaborators. They can, for example, if you are multiplying m different block encodings, usually you would expect to have log m number of additional ancilla qubits. They recently showed that if you are okay with doing that, not exactly you can prove a lower bound, but if you are okay with doing that approximately, then using, I believe, k ancilla qubits, where k can be a constant, you can achieve 2 to the negative k accuracy. So I think that's definitely something can be done. But in my current work, I haven't pursued that direction yet.
Yeah. Thank you.
Thank you. Thank you.